A child with mass 30 kg sits on the edge of a merry-go-round at a distance 3 meters from its axis of rotation. The merry-go-round accelerates from rest up to 0.4 revolutions per second in 10 seconds. If the coefficient of static friction between the child and the surface of the merry-go-round is 0.6, does the child fall off before 5 seconds? Alright, so here's the child, here's the merry-go-round, so we are looking at it from the top. There's the child sitting at a radius of r of 3 meters. Alright, so there's the centripetal force to keep the child. So at speed v, the centripetal force needed is v square mv square by r, and we'll say the maximum centripetal force is provided by the maximum static friction force. So what we are saying is this is the maximum speed the child can go at before the child will slip off, because the centripetal force is being provided by the static friction force. And Fs max, we know, is mu s times, and now looking at the normal force, this is the top view, and the side view would be, here the child sitting, there's the force of gravity, and the normal force would be equal to the force of gravity, equal to mu s times mg. Right, so we'll substitute that m v max square divided by r equal to mu s times mg. The math cancels, and so v max is r mu s g square root of that. Okay, so the maximum speed the child can go at before he or she slips is, so 3 meters times 0.6 times 9.8 meters square second square, and this is equal to 4.2 meters per second. So that's the speed at which the child will slip. Alright, now we got to translate that to angular velocity. Okay, let's add a page first. Alright, so v, the velocity, is equal to r omega, and omega is v over r. So this velocity is 4.2, so we'll call that max. Okay, so the maximum angular velocity at the merry-go-round can go before this, when the child will slip, is the following. So, and this is 4.2 meters per second divided by 3 meters, and this is equal to 1.4 radians per second. So that is the maximum angular velocity that the merry-go-round can have before the child will slip. Alright, so now they tell us in the problem the merry-go-round accelerates from rest up to 0.4 revolutions per second in 10 seconds. Okay, so we have, let's convert this to revolutions per second. or rather, let's convert this 4 revolutions per second into radians per second. Okay, omega final equal to 0.4 revolutions per second equal to 0.4 into equal to 0.4 revolutions per second, and 1 revolution is 2 pi radians. Okay, so 0.4 into 2 into pi is 2.51 radians per second. All right, so let's find the angular acceleration. Well, in 5 seconds. Okay, let's find omega final is omega naught plus alpha t. This is 0, so alpha is omega final divided by t, 2.51 radians per second divided by 10 seconds. So that, remember, this velocity was achieved at t equal to 10 seconds. All right, so angular acceleration is 0.251 radians per second squared. Okay, so now we just have to find what would be the angular velocity at 5 seconds. So let's add a page. Okay, t equal to 5 seconds, omega equal to omega naught plus alpha t. This is 0. The child starts off at rest. Angular acceleration is 0.251 radians per second square times 5 seconds. 1.26 radians per second. Okay, so the angular velocity needed to make the child slip is 1.46 radians per second, and at 5 seconds the merry-go-round is going only at 1.26 radians per second, so the child will not slip. At t equal to 5 seconds, the child will not slip. Okay. All right, that finishes the problem.